Hello everyone, this lecture is about topography and isostasy. As we've discussed last week, plate tectonics is taking place on Earth, and the surface of the Earth can be divided into approximately 15 main plates. These plates are separated by tectonic boundaries. They can be transform faults, ridges, subduction zones, and the plates can have continental material or oceanic material. On this diagram we discussed last week also, you can see the age of the oceanic lithosphere. What this diagram was showing you was that the age is young at the ridge because the material is being produced there, and it progressively becomes old when it's going close to the continental margins. The oceanic crustal thickness also varies from 0 to maximums of 30 kilometers in the regions of oceanic plateaus. The mean value is about 6 kilometers. Now if we focus on the continental side, you will see that the continental crust thickness is about 1 order of magnitude larger than the crustal thickness. So this map is showing you the crust thickness, and you can already spot regions where the crustal thickness is very large, such as here in the Andes, or here the Tibetan Plateau. You see on this scale that the thickness can excess 60 kilometers here. This map is showing you the crustal thickness in Western Europe. So you can recognize the geographical boundaries here from Spain, France, UK, and Norway here. On these maps you see that the maximum values of crustal thickness, which are in these dark brownish colors, are located in regions of mountain belts. So you can see here the Alps, and here you see the Baltic Shield. The Pyrenees can also be seen on this map. So last week we discussed about the lithosphere. Remember, the lithosphere is basically the crust plus a part of the upper mantle, which we will call here the rigid mantle. This the lithosphere is also the thickness of the lithosphere also varies and can be mapped, and that's again the map of Europe, which shows you the depth or the thickness of the lithosphere. So that's basically showing you the depth at which we have the transition between the lithosphere and the asthenosphere depth. And you see here a large variation on this map from about 50 kilometers, that's this color here, this pinkish color, to 300 kilometers. Again, you nicely highlight here the Baltic Shield, for example, but you can also see that in the Alps you have a thickened lithosphere-asthenosphere boundary. So now that's a very nice picture of the Earth that shows you an exaggerated topography. So don't freak out, that's not the true topography of the Earth, that's exaggerated by factor 100. The mean ocean depth on Earth is about 3.9 kilometers, and the mean continental height is about 700 meters. So how do we know that? Actually, here's an historical outlook, and that's how the first map of ocean floor bathymetry was constructed back in the 50s by Hisen and Tharp. So you see a subdivision here of a global map, and There are little squares with different numbers that will be basically regions that were mapped independently and then were put all together to map the topography of the Earth. So that's a painting here by Biren, made after the map which was constructed by Hisen and Tharp, and that's a very popular picture because it's one of the first representation of the bathymetry and topography of the Earth all together. You can see very prominent features on the map. So, for example, on the continents, you see on the orogens basically, and for example the Tibetan Plateau here, and you can see also very nicely very important features that stick out. These are the mid-ocean ridges. So one of the main author of this work is Mary Tharp. She passed away in 2006, and she was an oceanographer and cartographer, and her contribution is essential here because in her work she discovered the mid-Atlantic ridge by mapping out the bathymetry of the ocean floor. And this was a very important discovery because it really helped to push further the plate tectonics theory. You know that the ridges are an essential ingredient of plate tectonics. These are the regions of the divergent motion of plates and generation of oceanic lithosphere. Some decades later, here 2016, you see the same type of representation, a bathymetric topographic map, but this time applied to Mercury. So we are now able to map the topography of objects which are 186.23 million kilometers away from us. So that's very impressive. So let's go back to Earth. This is the eTopo data set that you can access online. This data is open. So we're just plotting here the topography of the Earth with the current data available. So the first thing we see is a smooth gradient in the ocean. So this reflects the motion of, or the generation of material at the ridges, and the progressive divergent motion of oceanic lithosphere away from the ridge. So you see the smooth gradients. There are regions of deep or sharp trenches. For example, here the subduction trenches are very nicely marked in the Pacific region. And there are regions of high elevation. These are located in continental area. Again, these are the plateaus that you can see here. So let's zoom on one of the plateaus. The Tibetan Plateau is the most prominent. For the scale here, that's about 1,000 kilometers. And the Tibetan Plateau surface is about 2,500 kilometers by about 1,000 kilometer width. So that's a huge object. It's the point of highest elevation on Earth, and this is the result of the collision of India with Asia on that side. Impressive topographic features can be also observed in the ocean, as stated above. So now we go back to the transition between the Pacific plate on the right side and the Philippine and Mariana plate on the left side. So you see a very nice trench marking the subduction zone. The Pacific plate is being subducted below the Philippine plate, and this is the region of lowest elevation on Earth. These are the deepest trenches. So if we go back to Europe, now let's have a look at the elevation. And what you see here on this map are regions of very high elevation. And these are, of course, at the current day, the Alps. So the Alpine arc is marked here in saturated colors, purple, pinkish, and the Pyrenees. You can also notice a very dark green region here, and these are altitudes which are at 0 or just below 0 level of the sea. So that's the lowest altitude in the Netherlands. Now we've discussed topographic maps, we've seen crustal thickness maps or more depths, and lithosphere, asthenosphere boundary maps. And if we look at regions such as the Alps, we actually see a correlation between the highest topography, the largest crustal thickness, and the deepest lithosphere, asthenosphere boundary depths. So there is a first order correlation between the thickness of the crust and lithosphere and the topography. That's what we want to discuss further here. So now let's think about the continents on which we would have an orogeny. So we have an immerged domain here above the seawater level with mountains, and below we have mantle and crust with the thickness of the crust that can vary. So that's a very sketchy representation of an orogeny, but there is also a very well-known example of such configuration, and the question is, do continents float like icebergs? So let's have a look at this picture. You see an idealized picture of an iceberg here. That would be the tip of the iceberg sticking out of the water, and this is the root. To explain such a geometry, one will rely on a theory which we call the local isostasy. The local isostasy relies on a couple of ingredients, the first being a simplified force balance. So let's have a look at this simplified force balance. So in this sketch, you have a column here of material. This will be our iceberg. It's sticking out of a surface, which would be the surface of the water, and it's extending down to a certain depth. So we have the density of the material, which will matter, if it's density of rock or if it's density of ice or density of water. There will be differences. The gravity acceleration will be important. Delta A is the cross-sectional area of our block. So it would be a cut along the iceberg section. Sigma YY is the total normal stress here. So let's introduce two forces. We have one body force, which is basically caused by gravitational acceleration, and this can be computed as rho g times y, the thickness or the depth, extent of our object, times delta A, the section. So y times delta A gives you a volume multiplied by rho and by g. This will give you a force in Newton. The second force is a surface force. The surface force will be a stress acting here on a surface, and the surface is the section of the iceberg. So the unit of a force and how to relate stress to pressure. A force, as you know, is unit Newton, and stress, a force is nothing else than a stress times a surface here. So we have the Pascal times the square meter. That's what you see in this equation here. The stress, sigma yy, times delta A. Pascal times square meter. Now we're going to make a force balance. So the force balance will be the sum of the surface forces will balance out the sum of the body forces here. So on one side of the equation we put the surface force, sigma yy times delta A. On the right hand side we put the body force, rho gy delta A. And you can already simplify this equation by crossing out delta A, and you obtain the expression sigma yy is equal to rho gy. Now we need a second ingredient for the local isostatic model, and it is called the compensation principle. So what is the compensation principle? It means that there is a depth at which the weight exerted by several columns of material will equate themselves. We call this an isostatic compensation depth. So let's have a look at our sketch here. We have our object here and we draw a line at the base of the object. We're going to call that the compensation depth. If we draw another column next to it, then this column, we will study it until the same depth, the compensation depth. This will be the column of material water. This is column of material ice. We have column A and column B. The weight exerted by the same column should balance out or equate themselves at the compensation depth. So A and B should exert the same load or at this depth level. That's an expression for the compensation depth. We will equate the load of column A to the load of column B, evaluated both at the depth of the compensation depth, YCD here. So let's do that. This will be the weight of the iceberg and the weight of water. So this is in fact the application of Archimedes' principle to the iceberg. So any floating object displaces its own weight of fluid. That's why boats are able to float on the sea, for example. Same applies to iceberg, and same will apply to some extent to the Earth. So let's apply this principle to the iceberg case. We go back to this picture. We have one density, the density of ice, and one density will be the density of water. So we have different thicknesses here. The iceberg has a tip which is sticking out and which we can measure. Let's say the iceberg is 30 meters high. But we also know there is a root in the water, and we don't know the thickness of this root, and we are looking for it. So this thickness, HR, is so far unknown. Let's compute the total load of this column. It will be density of ice times G times H, the thickness of the part that sticks out, and HR, the thickness of the root. The same can be done for an adjacent column of water. So our column B is now here, and we're going to compute the load of column B down to the compensation depth. So we have material of water density times G times HR, which is the root thickness of the iceberg. Now we equate the two loads and one get the expression rho ice times H plus HR equals rho water times HR. And then you can solve for HR and you get an expression that relates H, which is known, rho ice, and rho water, which are both known, so we can evaluate HR. In this example, you will obtain a relationship that HR is about 9 times H. So this would be 9 times thicker than the part that sticks out. So let's go back to Earth, and let's imagine that now our continents that stick out of the topographic map are actually floating on the sea of mantle. So we draw a very sketchy configuration here. We have the sea of mantle, so the green material here has density of mantle, rho m, and we have a yellow block here that sticks out, and it has density of crust. Now we use the mean density of crust of 40 kilometers, so we know this thickness here, and there's going to be this thickness HR, and we will try to compute basically the difference of altitude between this point and this point. So let's introduce some characteristic numbers. So the density of crustal rocks here for the continental crust is about 2,800 kilograms per meter cube, and the density of the mantle will be set to 3,250 kilograms per meter cube. So the mantle is denser than the crust. Now we set rho c, sigma c equals sigma m. So sigma c is the load exerted by the crustal column down to the base here, and it should be equal to the load exerted by a mantle column down to this depth here, the compensation depth. So on one side we have rho c g hc equal to rho mg hr. We can solve for hr, and hr will be hc times the ratio of rho c and rho m. Now let's compute delta H, basically this part here, and delta H is the thickness of the crust minus the thickness of the root here. So it's Hc times 1 minus rho c divided by rho m. Then you can plug in these numbers for the density of the crust and the density of the mantle, and you will obtain that the altitude difference of between continents and ocean is about 5.5 kilometers. That's a first rough estimate. So there are models of isostatic compensation, and these were proposed by different authors. The first family of models are called local isostatic models, and we will discuss the Airy and Pratt models. A second family of models are called regional isostatic models. These are based on elastic flexure. So what we discuss in this lecture will be local models, and this part, the regional isostatic models, will be left out for the lectures of master level. So let's discuss the model of Airy versus the model of Pratt. The hypothesis of Airy, which you can see on the left hand side, was that the crustal columns adjacent to each other have different thicknesses. So if you want to explain a topographic distribution, you introduce a variation of the thickness of adjacent crustal columns. So we know there is a plateau, and we make the assumption that below the plateau there is a different thickness of the crust with regard to the lowland region. So we have one density, that of the crust, and a second density, that of the mantle. In the hypothesis of Pratt, we still try to explain this difference in altitude between a plateau and a lowland, but we now introduce an hypothesis that the crustal density varies laterally. So we have one crustal density for the plateau and one crustal density for the lowland, rho C1 and rho C2. There is still mantle below of density rho n. So these are two contrasting hypotheses because one of them implies that below a mountain range there is a crustal root, and that below a rift zone there is an anti-root, which means that the mantle has been rising as the crust has been thickened. In the Pratt hypothesis, this implies no variation of the Morrow depth. It's constant below mountain, and below a rift zone it would be at the same depth, but the density, so the composition of the crust, would vary laterally. These two models contrast, but they are not incompatible, because we do know that rock types have different densities, and we also know that the crustal thickness varies laterally on Earth. And what you will do in the exercise, you will use a combination of both of these models to create a more accurate estimate of the altitude difference between continents and oceans. So you will be using a combination of these two models. So let's quickly discuss the limits of the approach. Remember this picture? It was the picture of a orogen here with the mountain chain here and a root below. That's how you could imagine it in a discrete way. So you have different columns of crust, and these columns of crust varies laterally. So that would be the hypothesis of Airy. And of course this is a very simple model, but also a very useful model, as it can allow to make first order prediction. But the limit of the approach is that there is no feeling of lithosphere resistance to deformation. The interfaces between the different lithospheric columns, they assume to be stress-free, so they would slide past each other without resistance. The overall real G of the lithosphere is not included into this model. And in fact, this model of local isostasy will not apply to all examples on Earth. And so that's why there is a regional isostatic theory that exists. And this one requires knowledge of elasticity theory and basically a flexural model, including a bending stiffness. So it's much more advanced to develop this model, and rather than using the local isostatic model. Just for an outlook of what you could learn in the optional master course, Dynamics of the Lithosphere, you could learn more about the development of the regional isostatic model, its application to natural cases, and basically you would learn more on how plates deflect under a load and how this relates to the Earth. So to summarize the lecture, we've seen that the Earth features spatial variations of topography and bathymetry. In order to explain the first order topographic effects, we can use Archimedes' principle applied to the Earth, and that's called the local isostatic model. There are two local isostatic models. One is Airy's model and the other is Pratt's model. The Airy model assumes that the crust thickness varies laterally. The Pratt model assumes that the density varies laterally. Both models contrast, but they are not incompatible, and in fact you can combine them. There are more advanced regional isostatic models that also exist, and altogether this can bring some nice quantitative explanation of the variations of topography and bathymetry on Earth. Thanks for your attention.